This time I will discuss uniaxially loaded short column. Short column means the column is relatively short compared to its lateral dimension. In short column, the failure occurs mainly like crashing. So if I have a column like here, if I apply some load, so it will fail somewhere here. Now, for long column, what happens? For long column is typically cylinder. If I apply some load, it may buckle. You know, there's some buckling, and that is for long column or cylinder column. I'm not going to details about that definition. You saw it in your strength of material class. Simply, if the length is long compared to this lateral dimension, then it is a cylinder. So in this discussion, I will start only short column, which doesn't buckle so much, small buckling or negligible buckling. That is called short column. And inside short column, I will talk about uniaxially loaded. That means load will be only at the centroid of the reinforcement. There is no moment. There is no moment. If there is moment, there is another chapter. We will discuss it in the next chapter. Here, only uniaxially loaded. Okay, so two types of column commonly we use. One is tied, one is spiral. In tied column, the main reinforcement are tied using tie bar. In spiral column, my reinforcement will be spiral, like continuous tie. That is called spiral. And the distance between two corresponding points is called pitch, or the distance between spiral. And for tight column, we call the spacing as a spacing. Okay, regarding the cross section, does always the spiral will be circular? No, it can be rectangular, triangle, square, any shape. Shape doesn't matter. Matter is all about tie or spiral. Same thing here. This can be circular. This can be rectangular. This can be square. This can be triangular. So it can have any shape. Okay, then if I go to next discussion is some common requirement. Some common requirement before starting, say this is a B, this is X. Okay, so I'm telling is uniaxially loaded. That means load must be at the center. Now it is not always possible. Like our ACI code says, if there is some eccentricity, that means if my load acts somewhere away, somewhere here, still though we may consider it uniaxially. But what is the threshold? Threshold is 1 is or 5% of A's for tight column. For tight column. Let me check one more time. It is for tight or for spiral. No, it is for spiral. So for spiral column, if my load acts 1 inch away or 5% of H away from center, it is still okay. We can consider uniaxially loaded, or whatever we learn is okay. For a tight, it 1 inch or 10% of H for tight. For tight column, it is 1 inch or 10% of my H. Okay, let me check again. Yes, I'm telling the right from the book. So if my load is away from 1 inch or 5%, whatever is smaller, then still it is considered uniaxial. Some eccentricity is okay. That is number one. Number two is reinforcement ratio. Reinforcement ratio, this time we call rho Z. Why G? G means gross. That means reinforcement ratio is area of my reinforcement. ST means steel divided by BH. Why BH? That means we consider the entire section. We consider the entire section. You can remember in beam design, when we design beam, we used to use AS divided by BD. We do not use A's for beam, but For column, it is gross area, the entire area, BH. This is why we call rho G. So that is the reinforcement ratio. Okay, so now we will talk about some general requirement of uniaxially loaded short column. I will use book so that you can follow better. So I am using from your book article 9.5. Article 9.5 from your book. If you, I'm not showing the book because if you use other book is also okay, this requirement. So first one says, what is the minimum amount of reinforcement we should place? Or what is the limiting value of this steel ratio? So minimum will be 1%, maximum will be 8%. So we can use minimum 1%, maximum 8%. If you use lower value, less reinforcement, your size will be so big. If you use higher value, your reinforcement will be so high, section will be very thin. But if you use so many reinforcement, section will be thin, it will be very difficult to accommodate the reinforcement inside a small section. So you should balance. Practical value like 2%, 3% is good. Yes, 2%, 3% is good for practical purpose. Like you can easily accommodate inside the section. But again, you have this option based on situation. Like if your reinforcement is so costly, material is very concrete material is very cheap, and huge section doesn't matter, that time you can use this. If cost doesn't matter but you want a thin section, then higher range is this. Practical is 2%, 3%, 4% also okay. But you understood what I mean. Based on situation, you can choose. But 2%, 3% is very easy to design and easy to accommodate. Okay, next one is, what is the minimum number of reinforcement? So minimum number of bar, it says if it is a rectangular section, if it is rectangular or square section, then minimum number should be 4. If it is rectangular or square, minimum number will be 4. And if it is circular, it can be 4 for ties. But if it is circular, it must be 6. 6 for spiral. So if it is circular, 4 is for tie, 6 is for spiral. Okay, then for triangular is obviously 3. Minimum should be 3 for triangular. Okay, so that is the minimum number of bar. Now size, what should be the minimum size? Minimum size, there is no requirement, but practical says 8 to 10 inch. So this minimum size should be around 8 to 10 inch to be practical. Now in the previous ACI standard, there is a requirement that minimum area should be 96 inch square. This requirement is no longer valid. Any size is okay, but practically 8 to 10 inch is okay. And 8, this is about 6 or 5 inch. So 8 means roughly this. It's not so huge. So minimum 8 to 10 inch. Okay, then what should be the tie or spiral size? This one. It should be at least number 3 if it is up to number 10. If main bar is up to 10, tie size should be, or spiral size should be at least number 3. If main bar is 11 or higher, then this size should be at least number 4. And this requirement is same for beam also. Okay, next is spacing. Before going to spacing, okay, next is spacing. Okay, I'm going here. So for tie, so this is again tight column. So what should be the spacing of this? Spacing. This is spacing. This is spacing. Obviously, minimum is obviously 1 inch, because if it is less than 1 inch, your aggregate will not go. So minimum 1 inch. So what is the required or maximum spacing? Maximum spacing will be 48 times D, or 16 times this D, or minimum column size. This lowercase d, it means diameter of the spiral, diameter of the tile, not spiral, diameter of the tile. 16 uppercase d, this uppercase d means diameter of the main reinforcement, this dia. Lowercase d means this dia, tie dia, or minimum column size, whatever the minimum size is. So you should take the smallest, that is the maximum possible. Then based on this, take a round number so that you can design easily. Now if it is spiral, spiral is this, what should be the minimum or max? So minimum is 1 inch, maximum is 3 inch. For spiral, minimum is 1, maximum is 3. But what is the required? To calculate the required, you need some calculation. So what is the required spacing? It is 4 AS DC, diameter of the bar ratio. It is calculated using this equation. Spacing required is 4 AS DC minus DB rho S A DC square. Now what is rho S? Rho S is 0.45. Let me check with your book whether I am using the right equation or whether I made any mistake or no. Okay, there is no mistake. Now I'll go one by one. So minimum is 1 inch, maximum 3 inch. What is the required based on this equation? 4 AS. What is AS? AS means area of spiral. Area of spiral. That means if it is number 3, if you use number 3, your AS will be 0.11 inch square. If it is number 4, area will be number, I forgot the area of number 4, most probably 0.19 or something, whatever is, you can see your book, that is not a problem. So that is just an example. What is AS? That is the area of spiral. What is DB? Diameter of the spiral. DB, diameter of the spiral. It's very simple now. Rho S is still ratio for spiral. It will come from this. Okay, AZ, gross area of the column section. I'm not going here or here. F times C, the strength of concrete. Fy, the yield strength of the steel. So I told everything except DC and A core. Okay. Now what is DC? Oh, DC means, so if my spiral is this and my spiral is here, DC means diameter of this core. That means here to here, out to out, again out to out of spiral diameter. That means if you deduct only the clear cover, whatever is left, the diameter is called this DC, core diameter, or name is core dia, is DC. What is a core? Area of the core. That means the area of this, just deduct the clear cover. If your clear cover is 1.5 inch all around, then deduct 1.5 here, 1.5 here, that will be the DC. And then pi DC square over 4 is your area. So hopefully you understood how to calculate the spacing of spiral. What is the minimum 1 inch, maximum 3 inch, what is required, this. Based on this, choose a round number. Okay. Now I will go to how to, what is the design equation. So design equation, say if it is a section like this, it has some reinforcement here, area of reinforcement is AST, say this is ACE, this portion is say B, then my gross area is BACE, gross area is BACE. My reinforcement ratio, say rho Z is AST divided by say AG, that means AST is rho Z AG. Now these are some basic information. Okay, so total is AG, steel is AST. Then what is the concrete? So concrete will be say AC, AC is AG minus AST. This is some basic geometry. This is area, means area of concrete, not area of the core, it's called concrete. Now if I apply some load, who will take the load? Concrete will take the load and steel will take the load. So if whatever load I apply, if it's say Pn, then my steel will take load, area times stress is load, and then my concrete, or write concrete first. Why concrete first? There is no reason. I'm just writing, or it's mostly concrete. Okay, so concrete area times the concrete stress. Why it is 8.5? You can remember from the beam equation, where my stress diagram was this, then we made it equivalent rectangular. This was 0.85 F prime C, that one. So this 0.85 F prime C came from that equation. That means we consider this equivalent rectangular, and from that we consider 85% of the ultimate strength is my failure stress in the concrete. Okay, so area stress, total is force, then my steel times yield stress. So area stress is load, area stress is load. So my total load is this. Now this is theoretical. To make it say make it design, we need to multiply some factor, strength reduction factor. If we multiply here, so this equation can be considered design equation. But again, what is this? Strength reduction factor, and then they are what we are doing are uniaxially loaded. That means load is at the center, but still some eccentricity may occur. To account that eccentricity, we multiply another factor that is called alpha. So we multiply another factor called alpha. This is eccentricity factor. Eccentricity factor. And this is strength reduction factor. You know it from your beam equation. Now we can rearrange this equation. This portion I can write Pu, whatever your factor load. This is alpha P. This portion, if I write say Az minus rho Z Az 0.85 F prime C, here rho Z Az F Y. Okay, let me turn off the light to see better. So what I did here, I replaced AST by rho Z AZ. Here AST rho Z AZ. Now we can use this equation or this equation. So at least write it down. These two equations are very important. We start our design from this equation, then sometimes we need to use this. When, I will tell you later. But anything else in this equation? Oh, what are the values of this factor? Yeah, you know that factors always changes. When a new specification comes, they revise the value. So we should not memorize this value, but some briefly. This value is high for spiral, low for tide. Why? Because spiral column is like tougher. Its toughness is higher because continuously reinforced. Very, if you want to fail it, it takes huge load. It like absorbs so many load before failure. Tight column is tight here, here, here. So it is not so tough compared to spiral. So this value higher for spiral, lower for tight. It is in your book, whatever book you follow, there might be different values. I can remember this value. These are most probably 0.85 for spiral, zero point 0.8 for tide. This value 0.75 for spiral, 0.7 or 0.65 for tide. It changes again. Do not memorize this value. But everything else is more or less you understand. Okay, so I will delete it. And then what are the design steps? So design steps. Step number 1. Obviously calculate your factored load. Step number 2, ROSI. Assume a ROSI, 2%, 3% or whatever. Minimum 1%, maximum 8%, or it might be given in the problem also. So step number 3, calculate AZ. How to calculate? Use this equation. So because you calculated it, it is almost known. ROSI you are assuming in step number 2. This is known. This is known. You assumed it. So only unknown is AZ. So calculate AZ using this equation. And then step number 4. Take a round. Take a size. That means whatever you calculated, you can use that, but round up. Say you are calculated that is a fraction. We do not want to make a fraction. But if it is a round number, good. Otherwise, you have this option here to say take a size. Step number 5 is whatever you took, if both are same, equal, then you do not need to revise it. If say you needed, for example, 299 and you are assuming 350 inch square, that means there is a gap. If there is a gap, then revise for AST. But okay, again, I should not give any value. Or what is these two equations? This step says calculate AZ, then take a size, whatever the size is, then use this equation. Use the, or maybe I confused you, or I should write it again. Okay. So AZ from this equation, P alpha AZ rho Z AZ 0.85 A prime C plus rho Z AZ FY. From this equation, find AZ. And then take a size, revise for AST, then use this equation again to calculate this, to calculate AST. So calculate, so find your AST here, okay? Then choose bars, and then 7 is tie, select a tie, spacing, do everything. Then number 8, detailing. Yes, detailing and checking. That means check your minimum spacing, check clear cover, check number of bar, check the reinforcement ratio, everything. Yes. So hopefully you understood. So in the next video, we will see an example. So again, calculate load, assume rho z. Based on that rho z, calculate az. Calculate az from this equation. Then take a size. Based on that size, find your ast from this equation, and then choose bar and place it. Okay, design your tie, choose a tie size and find the spacing, then do other detailing. So these are the short summary of column. In the next video I will show an example. Thank you.